Okay, so tonight I will tell you a little bit about the Find the Sky project, and I'll also, in some sense, close the loop on some of the things we discussed last Friday. So give you some examples of the kinds of activities for high school students that are done in this context. So Find the Sky is the name of my current main research grant, and I remember that one or two of you, when I gave my course, asked what it's like to how does a research grant work? What are the details? So I'll spend a few minutes discussing that. So Find the Sky is let's say the short title. The more technical title is Astrophysical Probes of Fundamental Physics, and you'll see why in a minute. So this is a project that is funded by the Portuguese Research Council, FCT. So you go through the usual process, you write a grant proposal, you submit it, when a call comes up, and then it's evaluated anonymously or semi-anonymously by various other people. To give you an example, in the case of this call, so FCT is organizing different panels. There's a physics panel, various engineering panels, and so on. And there's also several types of grants, some where you can get more money, some where you can get less. This one is the highest level grant that FCT has. And in the physics panel, there were, if I'm not mistaken, 44 proposals, and 6 of them were funded. So this is one of them. So they are fairly competitive grants. So I'm the principal investigator, so I'm the scientific responsible. In addition to the Center of Astrophysics in Porto, there's 3 other partner institutions, which have some researchers or PhD students collaborating with the project and dedicating, let's say, 20% of the time working in common projects. This is also fairly common in these kinds of grant proposals. There's a main institution, but there's some other partner institutions. So in this case, the partners are the Center for Theoretical Cosmology in Cambridge, Trieste Astrophysical Observatory, and the Institute of Astrophysics in Paris. And currently, so give you an idea of the size of the team, there are 7 senior researchers, so me and 6 others, 5 junior researchers, so postdocs, so people who finished their PhDs in the last 1 year to 5-6 years, 6 PhD students. There's at least 1 more coming from Germany in a month. We'll probably open a call for another PhD maybe in late September, October. And then there's 13 junior students. So these are either master students or even undergraduate students or first-year masters, which, at least in the Faculty of Sciences in the University of Porto, can do research internships during their undergraduate degree, starting in the 2nd year. And typically, when they do so, they have a supervisor, obviously, but they can also be formally associated to a project. And one of the goals is, if the result of their project is successful and that they can write a paper or at least a poster which they can present in a scientific conference, then you can use funds from this grant to cover those expenses. Whereas people who are not members of the grant cannot be covered by the grant. So you preemptively put in the grant people who you think might need such funds in due course. So there's 13 of them. Obviously, these students come and go, right? As they start doing projects, I add them to the team. Eventually, they leave the project, and at some point leave the team as well. And we have also several other external collaborators with whom we collaborate occasionally, but which are not formally part of the team. And also several interns that, again, come and go. And depending on the relationship they have with the Center of Astrophysics, sometimes they cannot be added to the team. They're just interns. So they're in a slightly different status. All this is bureaucracy that I can explain to you if you really want to know, but I'm not really keen on explaining bureaucracy unless I have to. Okay, and this project started in January this year. It essentially builds upon an earlier project I had called Cosmo Espresso, and the structure of it is more or less the same. A lot of what I'll say next more or less applied to the previous project. And again, to give you an idea, The funding that you get in this case was 245,000 euros. 250,000 is the maximum you can get. So when you make a budget, you try to get close to the maximum you can ask. But obviously, you need to make a reasonable budget, right? And justify everything you put there, because otherwise the panel can just say, this budget doesn't make sense, or it's inflated and essentially kill your application. So part of this is money for travel, for equipment, for other things. Almost half of it is funds for these 2 PhD grants. So there's 2 students directly funded by this grant. And it also includes the one item in the budget is essentially money for networking, for visiting secondary schools and for other activities with secondary school students. This is more or less common now. When I first applied to the Cosme Espresso grant, which was already 6.5 years ago, as far as I'm aware, it was the first time that the grant in Portugal had a specific item in the budget for education and outreach. Putting education and outreach in your grant is not uncommon, it's not new, but typically it's a sort of a side note in some other budget item. In this case, both in the previous grant and this one, around 7-8% of the budget is for this. And it's allocated for that, and you cannot use it for anything else. Okay, so the other important thing when you write a grant, and I'm sure many of you will be doing that in the future, is you need to have an overarching goal, right? Or at least a set of questions that you try to address in your research plan. Then below that, there's a number of details so which are the things you want to do specifically, like specific projects that the PhD students will work on. But you need to have let's say, a vision for the project. What are the things that you're aiming for? So these are the scientific goals of the project. So essentially, the way I formulated it when writing the proposal was in terms of 6 questions. And if you read through them, you probably recognize some of the things we discussed in my course, and you understand why I enjoy talking about them, because those are the things I do in my daily work. So the first is testing whether the laws of physics are universal or whether they are in some sense local. So there's several ways of doing that. One is to test whether fundamental constants like the Fine-Schwarzschild constant are really constant, or if they vary in space or in time or with local environment. So there's several ways to do this in astrophysics. The most common and the most precise one is to use high-resolution spectroscopy, and for this we have the espresso spectrograph that I described to you a little bit in one of the lectures. Then we want to test whether gravity is really just geometry or whether it's something different. Again, we discussed this in detail some days ago. Here, our contribution focuses on 2 things. So one, again, is using espresso. I didn't really cover this in detail, but you can use espresso measurements to test the behavior of gravity. The simple relation is that if alpha varies, then you unavoidably violate the Einstein equivalence principle. But there's a more detailed argument that one can make. On the other hand, we're also members of the Euclid satellite, which, as you probably remember, was launched on the 1st of July. And there, my contribution and the contribution of other people in the team is exactly to test the behavior of gravity using Euclid itself and also some other complementary probes that one can combine with Euclid. Thirdly, there's the slightly broader question of what is the physical mechanism behind the acceleration of the universe. Right? So you also remember that we discussed why understanding whether this was a cosmological constant or not was important. So again, that's something that we and a number of other people are trying to address. Here, our main contribution is trying to find ways of mapping the expansion history of the universe, so measuring the Hubble parameter, if you want to think of it that way, all the way from redshift 0 to redshift 4 by combining different probes. And one of them is the redshift drift, which again, you may remember from the classes or from one of the questions in the exam. Redshift 3 is not the working probe yet. No measurements or no successful detections have been made so far, but we believe that with the ELT and maybe other instruments like the square kilometer array, one will be able to do these measurements, and these measurements can contribute to this mapping. Then a slightly different probe, which I like because it's what I started my career on. That's what I did in my PhD, is to try and understand better the evolution of topological defects. And the connection with the rest of the grant is that if you detect these defects today, they're kind of fossil relics of earlier phases, because remember, they form during phase transitions and so on, so that they keep some information on earlier phases of the universe. And if we detect these objects and study their dynamics and understand how they work, then we can at least indirectly extract some of this information. And as you probably remember, there's two ways to study these objects. One is to do heavy computer simulations, and I told you that we currently have by far the fastest and most accurate code of this type. It was developed by one of my PhD students, who was now a postdoc in Helsinki. On the other hand, you can also do some analytic modeling. Again, you might remember the class or one of the questions in the exam. But the two things go together, because in order to calibrate the model, you need precise and accurate simulations to determine some free parameters in the model. So in a sense, you can only improve the model if you have better simulations. Or in other words, the precision of your model, or your model can only be as good as the simulations you have. And if you want to make detailed and accurate predictions for the gravitational wave background that these things emit, for example, then you need to have an accurate model, which means having accurate simulations. And here, something that I only mentioned very briefly, you can have various different types of defects, and in particular, even if you restrict yourself to strings, you can have various different types of cosmic strings. Some are charged, some are not charged, some have kind of superconducting currents. And the dynamics of them is, to first approximation, the same, but in detail is slightly different. And with very good astrophysical probes, you could actually, in principle, figure out, if you detect them, are they charged, are they not charged, and so on. There's a lot of fun to be had with those models. Again, I can explain later. Then, looking into the future, I also mentioned that you're never satisfied with the telescope or the spectrograph you have, right? You always want the better one. So now we have Espresso, which is a kind of new toy that we've been playing with for 5 years or so, but you're already thinking of the new one. And among other projects we're involved in, we're participating in the construction of the Andes spectrograph, which I also mentioned, which is in a sense the successor of Espresso. And it's high resolution spectrograph for the ELT, and it's the one which we believe will be able to detect redshift 3. So that instrument is currently under construction, is what's called the phase B of construction. And there's lots of engineers and so on working on it, but there's also a science team thinking of the science the instrument can do and trying to make sure that the engineers do things properly. And if there's bottlenecks or trade-offs that need to be done because of cost or technological limitations, we need to be able to provide advice and try to steer the project in the best possible direction. So here, again, just to give you a specific example, the science team has 100 people. The number of participating, so the consortium has 13 countries already, which contribute different amounts of human resources and funding and so on. The number of people from each country in the science team is proportional to how much you pay. But then with each country, you're there essentially according to your expertise. So there's 4 working groups, one on planets, one on stars, one on galaxies, and one on cosmology and fundamental physics. And currently I'm the chair, so I'm the leader of the fundamental physics working group. So in the previous phase, in phase A, Joe Liski, who you met, was the chair. I was the deputy. So now in phase B, I'm the chair, and there's 2 other deputies, one from France, one from Australia. And finally, the sixth point is on human resources, in a sense. How do we ensure that we have a next generation of researchers that can optimally explore the instruments such as the ELT that we are building now. So here, what we do is try to provide a bunch of student activities. Obviously, you're in one of them. Also provide mentorship in a slightly broader context. And again, in a slightly broader context, trying to involve high school students in scientific research. So there's this gap between school and university, which we discussed in detail last week. So we're trying to reduce this gap a little bit. It's better to leave it for the end because we're being webcast. So the project started in January. It's an active project. So just to give you a number, we already published 15 papers. Some are collaboration papers, so Euclid papers that have 200 authors, or Espresso papers which have 50 authors, but there's some people who are members of Find the Sky and which contributed. So I'll just give you three small highlights. So one is testing modified gravity models, so models that are alternatives to the standard model with dark matter and cosmological constant. You don't really know what these models are, and you don't need to know. You can ask me at the end. So this is essentially a project done by 2 undergraduate students during one semester. So one was a second-year student, the other one was a third-year student, and each one of them took one of these models and constrained them using proper statistical analysis. And essentially, the result that you find is that even if lambda CDM is not the correct model, it may be, and it probably is, just a convenient approximation to a true, more fundamental model. It's a fairly good approximation. So any model that is, or that wants to reproduce the data, must, at least at low redshifts, be very close to lambda CDM. You're not allowed large deviations because data will tell you it doesn't work. Then, so the second one is about forecasts for this Andes spectrograph, right? So as I said, as the instrument is being built, we're trying to optimize the science that we get from it. And this means analyzing various possible configurations. How does the science that we get out of it depend on the wavelength coverage of the instrument, on its resolution, on a bunch of other technical details. So we need to understand what is the best possible instrument that we can build, given limitations of funding and time and all of that. So there are several techniques that you can use to do that, some more sophisticated than others. One that is relatively simple but very useful is what's called Fisher matrix analysis. Essentially, you start with a model, with a cosmological model, in this case, that you assume is the correct one. You generate some simulated data that you think is representative of what the instrument can do, and see how well you could constrain that model with that data. And then we tweak, you scan the parameter space, you tweak various parameters, various assumptions, and see how things change, and can try to optimize your strategy. You define something which is usually called a figure of merit. What is the parameter that you want to optimize for? You want to get the best possible constraints on the matter density or some other parameter, and then feed that information to the engineers. They tell you what they can do, and you go back, run it again, and so on. So what we've done in this paper specifically is to study what you can gain from combining measurements of alpha and the redshift drift. So before we work, there were forecasts separately for each one of them. So we essentially combine the two. And one reason I chose this paper to mention is that my 2 co-authors, they're both called Katarina, and they were both students and monitors at previous AstroCamps. So Katarina, so the first Katarina is now my PhD student. The second Katarina finished her PhD recently in London at UCL. The third one, the more recent one, is not published yet. We finished it a few weeks ago, which is called a preprint. It's essentially testing string theory. In one relatively new idea in string theory is that the models that we have at low energy are some approximations, some limits of the true fundamental model. But not all such low energy models can come from string theory. And there's something called the swampland conjecture that says that any model that you get at low energies and which comes from string theory must obey some set of criteria. Again, I'm not explaining what these are, I can tell you later. And models that satisfy these are in what's called the landscape of possible models. Models that don't satisfy that are in swampland, right? So they're not good models. So the idea here is to see, using current data, cosmological data, but also measurements of alpha, if these swampland criteria can be correct or not. Because if you show that they're incorrect, you would show that string theory cannot be correct. So this is a possible way of testing this. And the result, again, this is a complicated plot, but I just want to show you what a scientific plot looks like. The result is that it's actually not trivial to satisfy this swampland criteria. So this is potentially a probe of string theory. And here measurements of alpha also play a significant role, because in some sense, they are more constraining for this purpose than traditional cosmological data like supernova measurements and other kinds of things. Okay, so finally, let me get to the schools part. So this sixth item in our broad vision, which is what we call, slightly jokingly, find the schools. And phi, by the way, it just refers to the fact that a lot of times when cosmologists have to invoke a scalar field in their models, they use the Greek letter phi. So if you say phi to a cosmologist, you'll probably guess you were talking about the scalar field. So the idea here is to take groups of students in schools and work with them in projects of 1 to 3 years. If you think of secondary school, you could think of a group of students starting in 10th grade, and by the end of the project, after 3 years, they'll be at the end of 12th grade. So during secondary school, they would accompany the development of the project. But of course, schools can jump in later, or students in the 11th or 12th grade can jump in, and so on. So all these projects will have some relation to our scientific goals. And our ultimate goal, if you want, would be that by the end of these 3 years, the students would actually know enough to actually contribute to the research that we do. So obviously, you're not going to know things like general relativity, but you should be able to learn some coding, some statistics, and actually do some meaningful tasks for the project. So that's our goal, if you want. So how does it work? So I should say, I put this at the bottom, but it's probably better to say it now. We mainly thought of this for Portuguese schools, but in principle, there's no reason why schools in other countries can't join. And in fact, from October, we should have 2 foreign schools joining the project. So there's several components. So first, members of the team, so me, other senior researchers, PhD students, can visit the school. So once every 2 months, 3 months, and we can have activities for the whole school, maybe give a talk to 3 or 4 different classes. We go to the school gym, and simultaneously work directly with the smaller number of students that are part of this project, maybe 5, 10 students. There's also remote support. So we have a Discord server for the project that researchers and students are part of, but school members can also join it and see what we're doing. On the other hand, students from this school can visit us at the Center of Astrophysics, do what's called job shadow. So they spend 1 day with us, and each student follows one person. So this is the best way. So if you want to know what it's like to be a researcher in astrophysics, a simple solution is just follow me for a day, right? If I go and give a seminar, you come with me and sit in the audience. If I'm talking to a student or discussing things with the student on the blackboard, you sit next to us and see what you're doing, and so on. So we can have small groups visiting us for a day. We have funds to go to the schools. We don't have funds for the schools to come to us, because school teachers or school students are not members of the project. And as I said, the project can only fund its members. And then if everything goes well and the students progress, we could think of other activities like internships, access to telescopes. So if you want data to do some specific thing, we have contacts and we can give you or try to get you telescope time, access to other events, participate in scientific conferences that we organize, and so on. In terms of requirements, in addition to the interest and motivation of the students, there must be some formal commitment from the school, essentially from the school director or its equivalent. There must be some workspace which the school can provide, basically just a room that is free a few hours per week, some computers, ideally, and also one or more contact teachers, ideally physics teachers, that can ideally help the students locally, although, as I said last week, sometimes this is a bit of a bottleneck because physics teachers are not really well prepared. So finally, let me give you some examples of projects that some schools are doing or did. So all these 5 are examples where there has been previous success. So we know that students can do this on a reasonable time scale if they're sufficiently motivated. So the first one is essentially about coding solar system orbits, just in Python. And you can go in several directions. You can calculate eclipses, you can play with the precession of Mercury's perihelion and play with relativistic corrections and see how they arise and so on. So this is essentially a coding project. Next one is coding plus data analysis. You can take type 1a supernova data and prove that the universe is accelerating. So essentially reproducing the work that gave the Nobel Physics Prize in 2011. By now, actually, you have data that is far better than the one they had back in 1998. And you can show that this dark energy must be very close to a cosmological constant and so on. So you can also evolve in several different ways. Then you can build a Foucault pendulum to determine experimentally that the Earth is rotating, or to measure the latitude of the place where you are. Okay, so this is mainly an experimental project, some data analysis as well. Building a cloud chamber, which I mentioned to you in the course, so you can count the fraction of muons that you see as a function of altitude above sea level and do a test of special relativity. Again, this is an experimental project, but with a bit more data analysis than in the previous one, because you have to do it blindly and several other things. And finally, you can build an astrophysical spectrograph, a relatively small one, but at conceptual level, not that different from espresso. It's like a tiny little miniature version of espresso. And you can use to take spectra of bright stars, or you can also use it in the lab for chemistry and other things. So these are some examples of projects that we support and mentor. Occasionally, schools or students come to us and propose some other ideas. We try to give them feedback, whether they're feasible, they're not feasible, how much time it would take, what would be the cost, and so on. But in principle, we're happy that people come with their own ideas and so on. And that's what I have to say. So as you can see, we're trying to narrow this gap a little bit, and we're very keen to work with schools and get them involved in this. So that's it for today, and I can take questions.